So last time we talked about liquid chromatography and its components of a liquid chromatograph, right? And you just had a quiz on the kind of the flow diagram and some aspects of a liquid chromatograph. Now we're going to focus more on just what's inside. What did we call this in the flow diagram, Alyssa? You wouldn't know unless you played with the instrument, but I think I might have the column. Okay? So now we're going to talk about what's inside here, inside the analytical column, we're supposed to call it because it's worth so much. Andy, what, forgot my question. What's inside here?
Is it an electrode or?
Electrode is electrochemistry.
Okay.
That'd be like potentiostat. I think you'll mess with that later.
Is it silica?
Let's pop it open and look. Oh wow, someone did some digging in there. Right? You can kind of see. It should have been all the way packed to the end, but you can kind of look in there and see.
What is it for?
Yeah, what is that stuff?
It's like powder.
Now, if you have really good eyes, you can. Oh, this one. This one's the same thing. It's like a powder. Yeah.
No.
Looks like. Okay. Now remember, this thing costs $400, so they are even higher, and it's packed. Now this one's destroyed, and that's why we're passing it around. It's clogged and it's just pretty much trashed. But just by opening it and making that little gap, we messed them up. But if you look at a scanning tunneling microscopy picture, these black and white images, that's a real zoomed up image of what's in there. So they've moved way beyond packing with chalk. Now you have to have really good eyes. Alyssa, you have really good eyes. See if you can read what the thing says, the column. There's this print, and I don't know why they make the print so hard to read.
It says Eclipse XDB C183, C18, 3.0 millimeters times 15 centimeters PN.
Okay, no, don't worry about the pin, that's a part number. So the 15 centimeters must be what? The length of the thing. She said 3 millimeters.
The diameter
Of what?
of the column inside.
Inside. Okay. Now, and then she also said C something.
C18.
C18. Okay. Andy, read yours.
This is ODS hypersil 5 micrometers, 100 by.
Okay. Now, okay, keep going. Let's let him finish it.
2.1 millimeters. There's a little arrow. This is flow on the number, and this is fluid packet.
Yeah. Okay. He had 2.1 millimeters. So this column must be more smaller, narrower, right? And he said, what did you say? ODS or something? Or was that?
ODS hypersil.
ODS
5
hypersil.
micrometers.
And then Alyssa said, not ODS, but she said C18. Is that the same thing? C18 ODS. ODS is octadecyl silane. Octadecyl is how many? Is what number? 18. So they're both similar. So 18 what?
Is that carbon?
18 carbons. They're talking about 18 carbon atoms. So 18 carbon atoms where?
Is it talking about the stationary phase?
It's talking about the stationary phase inside that 2.1 millimeter column for Andy's anyway. Now this 18 carbons, does that sound like on the real organic end, or does it sound like it's on the inorganic end? Organic. Does it sound polar or nonpolar? Sounds nonpolar, right? 'Cause all the time was carbons. Okay, so and then Alyssa's didn't talk about microns, but Andy's did. He said 5 microns. So if you take that diameter of that column, divide it by 5 microns, you get about 400, 500. So this 5 microns is the size of these little glass spheres, these little glass balls. Okay, and you kind of see them better in this diagram. And you can fit about 400 or 500 of them across the column. And on these little glass spheres, they coat the ODS. They coat the C18, octadecal. Okay, and they've gotten pretty good at it. And so since they're glass spheres, you can pack them really well and really uniformly. Now these are scanning tunneling microscopy, so you can they don't look like perfect spheres, but they're pretty round in nature in general, so you can really pack them well. So they get that nice uniform packing, and it's called partition chromatography because you're really going between your stationary phase is this organic stuff, and your mobile phase. And you can we'll play around with that in the lab, but that's what they say doing chromatography. You're messing around with your solubility, like dissolves like, and trying to get things that are more like the stationary phase will be retained more. So the most common type of liquid chromatography performed today is bonded phase chromatography. In this type of chromatography, the stationary phase is chemically bonded to what do we say? The stationary phase is the carbon stuff, the C18, and it's bonded to a, what was that little ball made out of? Glass. So this really shouldn't say particle. It should say glass sphere, glass ball, glass particle, so whatever you want to call that. Approximately 5 microns in size, in diameter. Okay, it depends on what. Alyssa's didn't even say how big her particles were. Okay, so how do they do it? They make these silane compounds, and it's in the literature, and we actually, I don't remember if I showed you guys this. Have I? Have you seen this? Where we jump down to it. Have you seen this? Where I put water on a glass plate versus water on a silanized plate. You ever seen this?
Oh, so like it didn't move, and I think you've shown this. Wasn't it PChem was more splattered and the other one was like a nice ball?
Yes. Yes. Maybe you're not a PChem. Yeah. Andy, you probably haven't seen this either. So you guys are gonna have to come up here and see it, because you have to draw a picture of it anyway.
Oh, I like the one you said.
You like what?
The one that you did just said.
Oh yeah, that one's coming up. Okay, so you have to come up and see this. So just come on up, because you have to draw pictures of it. Unless you can already remember, and you have your photographic memory, draw your pictures. So the idea is to permanently bond a carbon chain that's C18 long onto glass. And imagine if you did. I mean, it's a very thin layer, so I mean, these are dirty. But imagine if you did. What would be an application of it? Like this is typical glass. Oh no, this one's typical glass. This one's the one that's coated. Can you imagine what an application would be? Well, maybe I'll show you what they can do, and then maybe you can imagine an application. So on uncoated glass, just glass. So again, this is permanent, so you can try scratching it off, washing it, everything. these silanized components won't come off. So this is one that doesn't have it's non-silanized, just regular glass. You put some water on there, right? It runs around, right? Sticks and stuff. You put water on a silanized plate. All right. I should have left that on here so you can compare. Right? And you pretty much have to be right where you're at and look down at it, and you can see, they call it the contact angle. What angle does that glass meet the bead with? And it's huge for silanized plates. And then it just rolls around on there. It's really what's the word? God, it rolled around. Philic would be this one. This one's hydrophobic. Look at that, nothing stays. So, what could be an application of this?
Windshield.
Bugs would come off really easy, right?
Maybe like radiation, protection from radiation.
Because that has to be something like lead. Could this fog up in the bathroom?
No.
Can't, because water's not going to stick to it, right? See, the idea here was, I always have these funky research project ideas. This was years ago. So I wanted to make these great big ones, and then I could put them in my bathroom, right? And then never have to. What I'm wondering, too, is could this stuff make a great big one and try tagging it, spray paint? Well, maybe it'll just wipe right off, right? So there's a lot of applications. Make a windshield out of it. Except by doing the research, though, we found that it's really involved and it's very smelly, very, really unhealthy process in making this. So we just made these little guys. It all had to be completely contained. And then we coated some glass spheres, and it's hard, but you can get a coated glass sphere to float in water just due to its hydrophobicity. Okay. So you have this part done then, right? You made your little sketches? Okay. So what does this stationary phase look like? So the particle is your glass sphere. Glass is composed of what bonds? Between what and what? Silicon and?
Carbon or silicon oxygen?
Silicon oxygen. SiO. It's just a crystal and kind of amorphous structure, and depending on the type of glass. And you can, so this is all just a bunch of SiO bonds, right? Anyway, what they're saying is that, so these O bonds that's exposed just have a bunch of hydroxyls. And that's coming from the air, water in the air, and you just get, so it looks like glass, a typical hunk of glass or a little glass sphere, it just has a bunch of these OH on it. Would you characterize this? Because what we need to get to be thinking about is polarity. And would this kind of be a polar surface, or would it be on the end of a non-polar surface? How can you imagine that? See if you can get a feeling for this.
I think this over here.
Yeah, you have all these OHs here. Now it's not hydroxide in the sense where it's basic. No, it's just a little hydroxyl. Polar. Polar, right? Because oxygen is really electronegative. This should be somewhat of a polar end. Okay. Well, what they do. Yes, this is the uncoated. This is uncoated. So then, now it's in the literature, and you can do this yourself, but you're not going to do as good of a job. They have their secret ways of making every single one of these coated. And so what you do is, what are they coating it with? C18. So CH3, CH2. Well, that'd be CH2 connected, right? this is what you're connecting it with. So how many of those CH2s would there be? There'd be 16 of them, right? So you have 18 total. So you have this big, long organic chain. And this is what you're connecting it with. And I could actually even, that'd be kind of cool. I should have, just scan and paste it. It's probably a poster out here somewhere in the hallway. And you can see why it's such a unhealthy process. But so everywhere where you see a hydrogen, you pretty much just replace it with this guy. And that's a patented process. So now you're going to have a hunk of glass that's completely and permanently coated, right? This is a bond, a covalent bond. It's pretty dang strong. So you'd actually have to etch that glass and scratch it off to remove it, okay? Or some chemical bond breaking process. So that oxygen is still there, and then you'd have your CH2, 16 of them, CH3. So and it just keeps going like that, right? Okay, so it's a very hydrophobic surface. So this is your stationary phase. And this is what works really, really, really well. So you can, and this is just octadecal. You could have decal. You could coat this with whatever compound you want and modify your stationary phase. Okay. It's just that we just did octadecal because it's the most common and because it's the most widespread use, and you'll see it a lot. Because we're mostly interested in organic analytes. Okay. So Andrew, how would you answer this? Which stationary phase is referred to as a reversed phase chromatography? Polar, nonpolar, solid gas?
Polar.
What was the type Sweat used? He used polar, and we called that normal. So this one's going to be nonpolar, right? Because it's reversed phase. So this is what pretty much every laboratory is doing nowadays. So you have two columns. One is a C18, you know, like you'll see ODS, octadecal silane, right? Same thing. Then using the same separation parameters, so nothing has changed. The same mobile phase composition, the same flow rate, the same injection amount, everything is kept the same. The only thing they changed is the column. It's injected onto a C8 column. Okay. Sketch how these chromatograms may look. Now, the only thing that was injected was benzene. And I assume you have to assume the detector is set up to detect benzene. And benzene, I'm sure, absorbs in the UV, so they might just use a UV detector. But this is time on the bottom, right? And signal. So you have to start somewhere. Let's just say at 2 minutes, you get this nice sharp little peak. Okay, change columns to C8. Now what happens?
You maybe put fewer carbons.
Yeah, now there's fewer carbons, so it's less organic.
It's going to take more time.
So it's going to take more time. Everybody agree?
Yes.
Start out with thinking about benzene. Is benzene organic or inorganic?
Organic.
Organic.
So like dissolves like.
So like dissolves like. So you made the stationary phase, what did Andy say? You made the stationary phase less organic. Like dissolves like.
Yeah, that's going to take it.
Is it going to dissolve better or worse?
Worse.
Worse. So it's going to dissolve worse in the stationary phase. It's going to be retained worse in the stationary phase. It's going to adsorb worse onto the stationary phase, whatever words you like to use. So it will come out.
Dilute.
Well, they'll always come out more dilute because it's diluted by the mobile phase, no matter what type of chromatography. It'll come out faster, slower, same time.
Slower. Instead of 2 minutes, it'd be 4 minutes.
Back.
Oh, I know,
Faster
it's
because-
faster, yeah, because it's gonna stay, it's faster because there's less, right?
Less what?
It'll come out right away because
Less carbons where?
In the stationary.
In the stationary phase. So your
They'll go
these
through-
really organic analytes, they're less soluble or more soluble?
More soluble.
Less soluble.
Less soluble because there's less organic. So it's just kind of like this range of organicity somehow. And they don't use that word. I don't know. That's not even a word probably. But think about what they do say a lot is more organic, less organic. So you start out with your analyte. It's very organic. Very organic. So that means it's a straightforward proposition. If you make the stationary phase more organic, this will be retained much better. It's going to
spend more time.
It's going to spend more time in the stationary phase. Everything spends the same amount of time in the mobile phase, but the stationary phase, it's all different. And
that's where like the reading is taking place, like in the
at the
stationary phase.
at the very end of that flow diagram where that detector is, if the column does its work appropriately, then all the readings are done at the end, the detector.
Benzene is the analyte,
So benzene is the analyte, yes.
so it becomes less dissolved.
You could think of it that way. It becomes less dissolved in the stationary phase.
There's more-
But it's always dissolved to some degree,
So it's going to come out a lot more quickly.
much more quickly. Because
But the peak isn't going to be as intense.
yeah, well, that's a good question. What's going to happen to the area? You know, I think if you want to quantitate things, you can only change one thing at a time. So that means you just change the amount you inject, you make a calibration curve, and you calibrate. So I would think the area is going to be roughly the same, but I wouldn't compare the two. I wouldn't quantitate your results by injecting on a C8 column on a calibration curve I made on a C18 column. That doesn't sound right. Right? You want to change only one thing at a time, and that's the concentration of your analyte. So, but I would say it's roughly the same area, but it should be definitely only one peak. Don't worry about the area, but definitely only one peak because you're assuming it's working right, and it should come out sooner. So who knows? Just anywhere faster than 2 minutes, you draw it. So here's 2 minutes, and let's draw it faster. All right. This needs to come out faster than 2 minutes. Yeah, will it be, since it's less than half the carbons, would it be half? You know, now you're talking stuff that they really don't even care about because they're just going to inject it and find the answer. There's so many parameters to mess with. Just do the chromatography. So you have, doesn't matter, C18 or C8 column. So here it is. You have 2 minutes and less than 2 minutes for benzene. How could you make it elute even faster? What could you do? Well, I guess, English is always hard. It confuses things. What it means is either of these peaks. So that means that, how'd you get this peak? You have all these parameters. So they're talking about not changing the column anymore. That's what I'm trying to say. Now you're not changing the column anymore. But, so you change this, whatever you pick as an answer, you take this and you apply that to both of these situations, and it's going to come out even faster. So what's something that a chromatography parameter that you could change in both these situations, and it come out even faster for both of them?
Temperature.
If you crank up the temperature,
Increase the pressure.
well, one at a time. Temperature is just, I would say almost always, yeah, but then it could just make things fatter too. Temperature is kind of a dangerous one. That works for what type of chromatography though? Gas. That will be a perfect answer for gas. Definitely. Definitely for gas. It will always work there. But for liquid chromatography, oh. Okay, but you said
The pressure,
crank up the pressure. Now, how do you crank up the pressure?
the pump, you have to turn the pump to a higher
High.
power.
Yeah, but what's the word? You're getting there.
Force.
Yeah, more. It's pumping harder, more force. You're increasing the
Flow rate?
flow rate, right? So that would be super easy. That would be one way. Increase flow rate. There's one more easy answer. Well, general answer. Always work. And you got to think like a chromatographer. It'd be easier if you had an experience pushing the buttons. But just imagine yourself in front of this machine. Try to recall that flow diagram of all the components and buttons that you have. What could you do to make both of these situations even faster?
Change the mobile phase?
Exactly. Hang on, one at a time. Change the mobile phase. Okay. Make it more what?
Polar.
Make it more polar.
Make it more nonpolar.
Make it more nonpolar. Which one? You got to have a 50-50 shot at this. And remember, recall like dissolves like.
Nonpolar.
Make it more nonpolar because your analyte is,
Which is nonpolar.
which is organic, which is nonpolar. So just make the mobile phase more like your analyte. So that's the other really easy one. Make mobile phase more organic. Whatever word you like. If you like nonpolar better, yeah. I like the word organic because if you use the word organic, which solvent is more organic? Methanol or ethanol? Ethanol because it has two carbons. But they're both polar. I mean, they both have an OH. So you'd have to look at this little scale and what's their Debye, what's their polarity. No, if you stick to the word organic, life is a little bit easier. Okay, those were the two easy ones. Using a C18 column, a sample of gasoline was injected on the liquid chromatograph using a mobile phase of 45% ethanol, 55% water, and a column temperature of 30. Can this chromatogram be improved? So, we need a chromatogram first, so I should have had one in there. Signal, time. So let's say it's liquid, so the peaks are kind of fat, so you got some stuff coming out here. You just draw whatever you want. You'll see the picture. What I want to do is way out here, you have a couple things. All right, so you've got, I don't know, maybe this is 5 minutes. See if you don't need to draw it exactly like this. I'm just trying to get a point across. All right. Everything comes down to money. So time is money. Every run you're wasting 5 minutes of time. They probably really don't even care about the mobile phase you're wasting. It's just your time. You like it. Every run you get to sit there for 5 minutes and what could be done? With all you know is these separation parameters. So you don't know anything else, and you're using a liquid chromatograph.
Change the percentage of the solvent to mobile phase being used.
Change it to, okay.
So instead of 45, 55.
More organic solvent.
Okay, so what could you change it to?
70, 30.
Okay, just pick one, 70-30. Okay, so 70% ethanol and 30% water. Now, talking about change the mobile phase. Now let's say you go ahead and you did that. I guarantee you, you just lost this beautiful resolution right here. Remember, with this chromatograph, there's two types of runs. What were they? We called them blank and blank. Isocratic and gradient. So if you want to get out, try not to always think isocratic, because it's very linear, it's very easy. Oh, let's change it to 70-30, and this, no. What you could do is, remember, the whole system is open to you. You can 100% control you have. You could, after so much time, you could change it to such a percent. You can make it a real true gradient, or a real complicated gradient, where it's changing by it's increasing its ethanol percent 1% every minute. It's changing the flow rate after so much time. You have so many things you could do. So what might be safest is don't mess with this, because it's really hard to get it to look like that in the first place. You wouldn't know that unless you played with it, right? And then, so since after the first 6 minutes looks pretty good, and everything is somewhat resolved, and they're kind of running together, but after 6 minutes, then maybe crank up the flow rate or the ethanol percent, like you said, right? And you just want to be careful, because these guys will run together but you'd play around with it. See all the things you could do? And you don't know if it's going to work unless you try it. Okay, so that's what they mean when they say doing the chromatography. Some general ideas. Can you see the picture? That's when two liquids are what?
They're not soluble in chem.
Yeah. The I word? Immiscible. Yeah, insoluble works too. Immiscible is better for liquids. Okay. The pH less than 2 isn't good. pH bigger than 8, and this is all due to this bonded phase chromatography of attaching the stationary phase permanently to these little glass spheres. And that silica backbone has some trouble with those low and high pH ranges. Okay. We filter everything, because it's just a big plumbing system. I think you've seen the little plunger and the little filter you jam on the end, so that you have to filter everything, your standards, everything. They say this is bad. So there's upstairs, we have these log books, and there's ideas in there as to how to turn instruments on, how to shut them off, and these are some things that are in the HPLC handbook. That if you're using a buffer, and a lot of times you don't want to reinvent the wheel. You just go to the literature, you find, oh, this dude used this column, he used this mobile phase, and one of them was a sodium phosphate buffer at this concentration, at this flow rate. And you just copy it, right? And then you modify it a little bit to get good resolution. And the point is whenever you have buffers, you want to run the system through with some organic solvent, ethanol, isopropanol, whatever, because you don't want to keep buffers in your column. Blank is the diagnostic tool in liquid chromatography. Pressure. Yeah.
Answer's right there.
Yeah, I know. I just removed it. Next semester's not going to have it. Separations are more complex than liquid chromatography because you have an interaction, and their peaks are fatter, resolution's tougher to get. But the advantage is is there a compound that you can't do it with? No. So it's good for everything. Okay, so that's all we really have.
The Wikipedia I was reading, it said reverse phase chromatography